In this video, we will look at titrations and calculations involving titrations. Now, if you haven't watched yet the previous video on solution stoichiometry, I'd strongly encourage you to click on this banner link here and go back and watch it, because a lot of the concepts there apply here as well. But for titrations, what is a titration? A titration is a very specific technique. It's an analytical method that we use to determine the concentration of something that we don't know the concentration of by very carefully reacting it with a solution that we do know the concentration of. We call that a standard solution. When it comes to titrations, there are two ways that we can measure this meeting point. One of them is something called the equivalence point. The equivalence point is the exact stoichiometric point that occurs within a chemical reaction in solution. So when the moles of the acid or the base equal out with each other, or whatever it is that we're reacting with, that is our equivalence point. Now, equivalence points are very difficult to obtain experimentally, other than using something like a pH probe or some other kinds of software. They're hard to do just by kind of looking at them. What is much more clear and much easier to do is to find the endpoint. And the endpoint is when we add an indicator to a titration and the indicator changes color. Now, usually these 2 points are really close to each other, within a tenth of a milliliter, maybe even less sometimes. So we can tend to estimate pretty well the equivalence point by finding the endpoint. And we do so using something called an indicator. An indicator is used to give us this estimation of the equivalence point through this change in color. Now, the most common indicator that we use in chemistry lab, at least in general chemistry lab, is phenolphthalein. Phenolphthalein will show this colorless, clear color in solutions that are acidic. It'll show this dark pink color in solutions that are basic. And somewhere in between there, you get this lightish pink color that we use to approximate when the end point is. There are other indicators out there. Methyl red is an example of them. In Chem 106, Gen Chem 2, we'll talk extensively about indicators and what kinds of indicators are appropriate for what kinds of situations and so on. Now, you may recall this from our previous video. This is our mole map. We used the mole map in chapter 7 to help us to organize our stoichiometry. And in the previous video, we showed you how you can manipulate that mole map for concentrations and solutions by using molarity as the way of going between volume of solution and moles of the solute of that solution. And once you get to moles, then it becomes like any other stoichiometry problem. Now, luckily for us, in titrations, we don't actually have to do this, because we can actually sneak around a little bit if we keep our volumes consistent. That is, we always use liters or we always use milliliters. If we can keep that consistent, then we can very easily interchange and go between molarity of one solution and molarity of the other solution, which is usually what we're trying to find in titrations. And so this kind of skipping across the middle, which usually does not happen in stoichiometry, can happen in titrations, and it does so using something we call the titration equation. Now, the titration equation should look familiar to you as well. In a couple of videos ago, we looked at dilutions, and the dilution equation was M1 times V1 is equal to M2 times V2. Well, this is in the same kind of vein, only instead of M1 and V1, what we keep on one side of the equation is all of the information that we know about an acid. And on the other side of the equation, we keep all that we know about the base. And so if I know the molarity of the acid and how much of it I use, and what the balanced chemical equation looks like for the acid, and I know the same data for the base, I can solve for whatever is missing. What's also nice is that this doesn't have to apply just to acids and bases. You do an example of a redox titration in the laboratory, and you can do this and substitute the oxidizing agent for acid and the reducing agent for base, and the titration equation works just the same. So let's take a look at a couple of examples. In this first example, what is the concentration of sulfuric acid if 15 milliliters reacts with 18.45 milliliters of a 0.0973 molar sodium hydroxide solution? Now, you might be compelled, okay, well, I know the dilution equation. I'm just going to throw this in here right now. I need, let's see, 15 milliliters of, acid times its concentration, which we don't know, is equal to 18.45 milliliters of the base times its concentration, 0.973 molar, and solve for molarity and come up with an answer 18.45 times 0.0973 divided by 15. Okay, if you did this and you came up with an answer like this, 0.120 molar, you would get the answer wrong. Why would this be considered wrong? Well, you haven't taken into consideration the stoichiometry. Stoichiometry always matters. The balanced chemical equation always matters. It's not always going to be true that these are going to react in a one-to-one fashion. So, like with any other stoichiometry problem, even ones that can be kind of cheated with equations, we need to start with a balanced chemical equation. Balanced chemical equation would look something like this. H2SO4 reacts with 2 sodium hydroxides to make 2 waters and sodium sulfate. There's my balanced chemical equation. And the reason why that makes a significant difference now we set up our calculation, molarity of the acid multiplied by 15.00 milliliters divided by 1 is equal to molarity of the base, 0.0973 molar, multiplied by 18.45 milliliters, divided by 2, the stoichiometric coefficient for the base. And if I do that, algebraically, I am going to need to get rid of the 15. So I'm going to multiply each side of the equation by 1 over 15 milliliters. And so doing that, my milliliters cancel on the one side and the 15 milliliters on the other side. The answer here, 0.0973 times 18.45 divided by 2 divided by 15. I get the molarity of the acid at 0.598 molar. Now, this is about half. Remember, we came up with about 1.2. This is about half of the concentration that we would have calculated if we just plugged it into the dilution equation. That's why it is significant. That's why we need to do our calculations correctly. Now, the other thing that we need to point out here, the importance of our units. If our concentration units are the same, if our volumes are the same, then it really doesn't matter what we do. We're going to input molarity, we're going to output molarity as a result. We're going to input milliliters, we're going to output milliliters as a result. So long as we keep it consistent, we'll have no problems whatsoever with the calculations. Let's take a look at another example. If it takes 21.33 milliliters of 0.1199 molar sodium hydroxide to reach the endpoint of a reaction with 25 milliliters of an unknown concentration of hydrochloric acid, what is the concentration of the hydrochloric acid? Now, in this one, we've been given a chemical equation. Is it balanced? Well, quick inspection, I've got one sodium and one sodium. I've got one chloride and one chloride. I've got a hydrogen and a hydroxide, and hydrogen and hydroxide make water. Looks pretty good. So from this perspective, I have the balanced equation already. I can get right into the solving. Once again, I do not know the molarity of my acid, but I do know that I have 25.00 milliliters of that acid, and the stoichiometry here is a 1. And on the flip side, I have 0.1199 molar sodium hydroxide and 21.33 milliliters of that sodium hydroxide. And my coefficient here also is 1. So spitting out my algebra here, I know I need to divide each side by 25 milliliters. And so if I do that, 1 over 25.00 mils times this fraction times 1 over 25.00 mils. My 25 mils cancel on the left side. My milliliters cancel on the right side. I'm left with just molarity. And so the molarity of the acid is equal to, we've got 0.11199 multiplied by 21.33 divided by 25 to 4 significant figures. I get 0.1023 molar HCl. So titrations really do make it easier because we don't have to go through all of the sloppy stoichiometry and all of the conversions in and out of molarity. We have a nice tight equation that we can use that will help us to really do the calculations quickly if we use them correctly. And you got to remember the if we use them correctly part really falls in that denominator. Are you using the stoichiometric coefficients? If you forget that step, it's going to be very hard to do the answer and to do the process correctly. But that's all for right now. Have a good day.